Food crops such as sugarcane and squash are produced and consumed worldwide. Many of these crops are treated with various fungicides in order to provide protection against disease. However, copper fungicides using nanocopper compounds such as copper oxide and copper metals may contaminate agricultural soils or water supplies via runoff. Carlos Tamez, a PhD student at the Center for Environmental Implications of Nanotechnology at UTEP, is currently studying the potential effects of copper nanomaterials on these crops.
Annually, Americans consume nearly 70 pounds of sweetener that comes from cane or beet sugar. According to the UN Food and Agriculture Organization, sugarcane was the top commodity produced in the world by mass at 4.4 trillion pounds. Squash production in the US alone is nearly 570 million pounds. Like all plants, these crops require copper, which is a micronutrient that plays a key role in the activation of enzymes and in the transport of electrons during photosynthesis. Copper is also often added as an active ingredient in fungicides and fertilizers. Industries also use nanocopper, which poses a serious contamination risk via runoff into natural waters. In 2010, nearly 200 metric tons of nanocopper was produced, with 25% of these materials ending up in either the air, soil, or natural waters. Our group focuses on nanocopper compounds such as copper oxide and copper metal, which are not currently approved for agricultural use, but still may contaminate the environment via their commercial and industrial uses. We aim to determine whether our food supply can serve as an additional exposure route. Due to the potential effects of copper nanomaterials, we performed a study on sugarcane evaluating plant characteristics such as plant height, root length, biomass, chlorophyll content, enzymatic activity, and copper uptake in the root stems and leaves. We planted mature sugarcane stem pieces in a natural soil mixture treated with one of 4 copper compounds, either a copper-based fungicide, a micron-sized copper oxide, a nano-copper metal, or copper chloride. The sugarcane was then grown in a greenhouse for 12 months. A similar study was conducted with zucchini with the addition of a nano-copper oxide. The zucchini was then grown in an environmental growth chamber for 3 weeks where we controlled light, temperature, and humidity. With sugarcane, we found no change in chlorophyll content, which is a measure of photosynthetic activity. We also saw little evidence of copper transfer from the roots into the aerial tissues of the plant, which shows the bioavailability of copper in the soil. This could mean that copper nanoparticles may not pose a hazard to our food supply. Copper transfer to the aerial tissues can be a good indicator of nanoparticle mobility within the plant structures. However, the plants were still in their immature stages and further development may reveal unforeseen effects. We did, however, see changes in enzymatic activity, which means the plant is producing free radicals which may cause cell damage or tissue damage. We also found no change in chlorophyll content or biomass with zucchini. Unlike the sugarcane studies, we did see copper transfer into the aerial tissues, but this did not seem to be causing damaging effects. However, increased copper concentrations in the aerial tissues could lead to food contamination. Our enzyme analysis shows a decrease in stress levels as compared to controls. This could indicate that some of the treatments are having a positive effect on zucchini. Moving forward, we'll be conducting long-term full life cycle studies on sugarcane. We'd also like to determine whether copper will transfer into the zucchini fruit or whether the non-edible tissues will accumulate copper while allowing the fruit to be uncontaminated.